So looking at the warm-up here, once again, you're asked to just plug in these x values from the t-chart into our cube root function now. So plugging those in for x, sometimes a little easier to do just by throwing your radicand in parentheses and taking it to the 1/3 power, as opposed to trying to do the cube root in the calculator. But we get this shape here, kind of like this S shape, Z shape. And you can see this one's going to extend all the way left, all the way right, as well as all the way down, all the way up, right? So both our domain and range are from negative infinity to positive infinity. So let's flip the page, look at the parent function. So as we look once again, looking at cube root functions, just the same as last class, looking at the square root functions, all that's changed here is our index values of 3, right? Or if we are talking about putting a fractional exponent on that same radicand, it'd be taking it to the 1/3 power. So the most basic of our cube root functions are this function f of x equals the cube root of x, right? Also could be seen as f of x equals x to the 1/3 power. So looking at the x values, that'll get you some nice y values to graph. Looking at perfect cubes now. So the perfect cubes we want to try to include and always get in our radicand, right, are the perfect cubes of, first one, -8. Then we have -1, 0, 1, and +8. So the cube root of -8, number times itself 3 times, it gets us -8, would be a -2. For the cube root of -1, we would get -1. Cube root of 0, it's just 0. For 1, we have the y value of 1, and when we plug 8 in there for x, the cube root of 8 would be a +2. So those values on the left there are the 5 perfect cube roots we're going to try to get in our radicand. So going back to our square root graphs, we talked about getting 0, 1, 4, 9 as the values under the radical. This time dealing with cube roots, we want to get the values of 0, positive and -1, as well as positive and -8. We're talking about cubing numbers. So you can see here, once you plot those points and connect those points, this time we can extend it all the way left and right through the points, as we're able to do negative values in the radicand since we have an odd root. Transformation still the same. A, H, and K transformations, just the same as before. All that's changed here is our index values. So looking at these next set of questions, trying to identify what type of transformations are taking place based on our A, H, and K shifts. So same as just before with the square root graphs. Now we just have changed the index value, but the A, H, and K still perform the exact same shifts. So looking at number 1 here, trying to identify A, H, and K. First step is to identify what each of those values are. So here out front, you can see our A value is a -2. Underneath the H value, remember H is always kind of opposite of what you see. So in this case, H value would be a -1. K value would be a 0. So it's a little confusing up here, but this is written as you would see it, right? So since we see the plus H, really we know that. That means the H value is a -1. So that way we would shift our graph to the left, right? So looking at that one, that's really going to shift the graph to the left one. Whereas this A value, since it's negative, is going to reflect across the x-axis as well as have a vertical stretch. Jumping down to number 3 now, kind of the same thing. Here, trying to identify A, H, and K. This time the A value up front really is that 5/4 fraction. Here, there's nothing in parentheses with x, so we know our H value has to be a 0. And then our K value would be what comes last, this -3 or -3. So just a couple transformations taking place this time. A value, even though it is a fraction, still bigger than 1, so we would have a stretch happening by our A value. So stretch by 5/4, and then with our K value, just -3, we would be shifting our parent function down 3. No shifts left or right on that one. Let's go ahead and try those even problems 2 and 4 with your group. So down here, number 5 and 6, we could really put these in either of these 2 formats, right? We could use the radical symbol with the index value of a 3 on it, right? Or we could throw the x minus h in parentheses and put that fractional exponent of a 1/3 on it. Both those really are the same thing, right? Just different ways to express a radical. I'm just looking at number 5. It says a cube root function is translated 5 up and 2 to the left. So each of those is a transformation. So the 5 up is affecting our k value, whereas the 7 to the left would be affecting the h value. So here, if you're thinking about moving 7 to the left on the x-axis, right, that would take this over to the value of -7. So now plugging in a h and k into our parent function. So for the first one, we'll go ahead and put it just in the radical, where you see the radical. So we'd say f of x is equal to, here, the cube root of x plus 7, and then plus 5. So remember, in our actual function, our h value is opposite as it appears. So that's why underneath we'd have the plus 7, signal our shift to the left. Look at number 6. It says a cube root function stretched vertically by a factor of 3, reflected over the x-axis, and shifted to the right 3. So just to show you, we could put these in either of these forms. We'll use our fractional exponent of 1/3 here. So the vertical stretch by a factor of 3, I know is going to affect my a value. Also tells me it's reflected over the x-axis, so I know that my a value has to be a negative value. So both those first two really are affecting a value. And then lastly, our shift to the right 3 will take me to the h value of a positive 3. So here for our function, we'd have our -3 in front of the parentheses, x minus 3 in the parentheses to the 1/3 power. Here there was no shifts up or down, so we don't need any k values. Just looking at the steps for graphing, pretty similar to the steps for graphing are our square root functions. All that's changing is once we determine our point hk, really that hk point is going to go in the middle of the table now, since this is going to extend all the way left, all the way right. Then we're going to find some values that are going to force the radicand to be those perfect cube values, both positive and negative, right? So you see those 5 values there we talked about earlier, -8, -1, 0, 1, and 8. Substitute those x values in to find those y values, which will allow you to graph 5 points and make that either S shape or Z shape. So we'll also talk about another method you could use, just kind of using the a value once you find h and k, to kind of use as the slope, going 1 to the right, and then also 8 to the right of your hk point. So to start here, identify h and k, put it in the middle of our table here. So if I make my XYT chart, here once again, I'm going to this time try to get 5 points. And then my middle point, I'm going to use h and k. So h always opposite is what you see under the radical. So in this case, I know my h value has to be a -1. K value in this case, there's nothing that comes afterwards, right? So my k value would be a 0. So right away, I know that that's going to be the middle point in my graph, sometimes referred to as the inflection point. So here at -1, 0 would be the middle of this S or Z shape. From here, trying to figure out these other values to plug into my x column that are going to give me some nice y values. So just like we talked about with our square root graphs, all we want to do is take the radicand in this case, the expression under the radical, which was x plus 1, and we need to get it to equal each of those 5 perfect cubes. So we needed to get it to equal -8, also to get it to equal -1, 0, +1, and +8. So once again, just by looking at your radicand, setting it equal to those 5 perfect cubes, you can see here if we were to solve for x, it's going to get us the x values we want to use. So here, all we need to do is subtract 1 to get these x values. So the first x value we want to use, -8 minus 1, takes me to a -9. So I know that's a value I want to throw in my t-chart. Doing the same operation. So really, if you want to write out the x plus 1 5 times, you're welcome to do that. But once you write it out once, you can probably figure out what operation you need to do to each of those perfect cube values to get the x values you want to use. So each time we're going to subtract 1. So the next x value I want to use would be a -2. Once I subtract 1 from 0, that gets me the x value that's already in my t-chart, right? That one would be a -1. Subtracting 1 again gets me my 4th one, which would be a 0. Plug that as the 4th x value in the t-chart, and then subtracting 1 one last time gets us our final x value we want to use, which would be a positive 7. So once again, finding x values that are going to get us that perfect cubes under the radical. That way, once we simplify that and evaluate, we can get some y values that would be easy to plot. So as we try to type these x values into our calculator, I think with cube roots, especially with the TI-30 calculators, it's a little bit more user-friendly to use the fractional exponent as opposed to trying to type in the cube root or put in the index value of a 3 on the radical symbol. So I would probably prefer to use this form of the function here, where we have this negative out front of the parentheses. Inside the parentheses would be whatever's the radicand, and then taking it to the 1/3 power. So it's probably a little bit easier to use, user-friendly with the TI-30 calculator. So once again, we're going to plug our x values in one at a time to come up with the y values that they're paired with. So you can go ahead and do that on your own. I will do that. So once we plug in each of those values, right, we get the y values that are paired with them. So go ahead and plot those other points here. So negative 9, 2. Slightly off the graph, negative 2, 1, 0, negative 1, as well as 7, negative 2. So once again, you should always make this S or Z shape. This time, since we had a negative A value and it's been flipped, we have the Z shape. Now we can talk about the characteristics of this graph. So it's nice about cube roots, right? They're going to extend all the way left, all the way right. So we know it's going to go all the way from negative to positive infinity. Same thing with the range, right? Eventually, if we zoom all the way out, it's going to continue all the way down to negative infinity as well as up to positive infinity. So the only thing that's a little trickier is making sure that you identify the range correctly, or the limits. So making sure you match up the limits with what's happening in each direction. So here, taking the values from my domain, once again, putting them under those little X to the arrows. It's asking us what's happening as our x values go to negative infinity, which would be off to the left. You're just asking yourself, are the y's going up or down? So off to the left, you can see our y values are going up. So up would take us to positive infinity. As we look at the right in behavior, or the right limit, we can see that as the x goes to positive infinity or off to the right, the y values would be going down. That would take us down to negative infinity. Increasing or decreasing intervals, once again, we're just answering one of these questions. As we track it from left to right, it's either going up or down. So here, as we move from left to right, you can see that this one's going to go down the entire time. So here we'd say it's decreasing across the entire domain. X and y intercepts, you can see a couple points we have here. X-intercept would be this point, negative 1, 0, whereas the y-intercept, where it crosses the y-axis, would be the point 0, negative 1. All right, so let's jump to number 9 here. I'm taking a look at another cube root function. One thing we want to do is just always be able to identify h and k, right? So I'm going to show you just another method you could possibly use. Some people find it a little bit easier, more helpful, especially if you struggle like operating the calculator here, finding h and k, then using your a value to plot the additional points, right? So first off, finding h and k. We find h and k as a positive 2, positive 1, right? So just from looking here, we can see h needs to be opposite, k needs to be the same. So we can come up with that value there. So I'm going to go ahead and plot that point here. So looking at it, hk, positive 2, positive 1. From here, what we can do is really use our a value, which our a value would be the value out front here. In this case, our a value is a positive 2, to plot some additional points, recognizing that our perfect cubes, right, were 0, 1, 8, as well as negative 1 and negative 8. So basically what happens here is your h value is going to get you this 0 under our radical, right? So h eventually just gets us this point here. And then to get our x values that get us the perfect squares, all we're going to have to do is add 1 to h, subtract 1 from h, add 8 to h, and subtract 8 from h, right? So if we were making our t-chart, instead of trying to plug it all in, right, we can just do some simple little addition and subtraction. So if my h value is a 2, All I would do here to get the next couple around it, I would add 1 to 2 to get 3, subtract 1 from 2 to get 1, right? So that gets me the next couple of perfect cube roots of -1 and +1 underneath there. From there, I'd go back to my 2 once again, add 8, which would give me a 10, and then subtract 8, which would take me to a -6. You could also count the spaces on the axes, right? So going 1 to the right gets me 3, going 1 to the left gets me 1, going 8 spaces now to the right takes me off to 10, 8 spaces backwards takes me to that -6, right? So you could count the spaces on the graph, right? Or just add and subtract 1 to the h value, as well as add and subtract 8 to the h value to fill out the x column of your t-chart. So once we do that, there's also a trick you can do to go ahead and plot the y values, right, as opposed to trying to plug it into your calculator. You can use the a value and start to apply it to the k, right? So looking at it, I know my k value is a 1. That point hk is in the middle of my graph here. So I know that if I go to the right 1 point, which in this case, if we're starting at 2, going to the right would take me to the x value of 3. So going down 1 row on my t-chart, all that would happen here is I would need to make sure that I add my a value to k. So whatever the k value was, all I'm going to do is add a to that. In this case, my a value is a 2. So once I add 2 to that, I would get 3. So you can check that also by plugging it into your calculator, right? Just like we talked about before. Sometimes it's easier to use that fractional exponent. But here, if we wanted to plug in x minus 2, take it to the 1/3, and then plus 1. So plug in your x values one at a time. You could come up with the y values like we just talked about, or start to use these a values. So if I added a to go in that direction, in the other direction, I'd want to subtract my a value from the k, right? So if my a value is 2, subtracting it once again would get me a -1. So if we go and plot those 2 points, you should see that they're mirrored across. So we have 3, 3, as well as 1, -1. So they should kind of be opposite of each other. Next, we're going to go to our next couple of points. All that happens here is we need to, going to the right, we would need to add 2a. Going to the left here, we would need to subtract 2a from k, right? So if my a value is 2, once again, in this case, 2 times 2 would give me a 4. So adding 4 to 1 takes me to 5, whereas subtracting 4 from 1 takes me to a -3. So remember, you're always going to do this to the k value, right, or that y value in the middle of the t-chart. You could also count the spaces, right? Like here, if I go to the right, I would go up whatever my a value is, which would be 1, 2. And then if I go left, I go down whatever my a value is, which would be 1, 2. Same thing applies here, right? As we move off to the point of 10, which I know is going to take us off the graph. But once we move over to 10, here we would go up 2 times the value of a. So from the 10 point, we'd be going up 2 and then another 2. So a total of 4 to get us this point here. 10, 5. And then in the other direction, going to -6 would be going down to -3. So these should also mirror each other. So when we connect them, we have this S-shaped cube root function. So the domain, once again, -infinity to +infinity. Range, also the same. All that happens here is you want to make sure that you match up the limits correctly, right? So if I take the left value in my domain, throw it underneath the first limit, take the right value in the domain, throw it under the second limit, and I'm going to talk about what's happening to my y values as they go in each direction, right? So as long as you do it that way, the first limit, we're always talking about the left limit or the left in behavior. Second limit, we're always going to be talking about the right in behavior. If you put the domain values in that order, left first, then right underneath those x's. So off to the left, I can see that this time, as I go further and further left, my y values are going down. So that's going to go down to -infinity. Then off to the right, my y values are going up as I move off to the right. So in this case, my y values will be going up to +infinity. This one, as we trace it from left to right, we can see is going up So we would say that that graph is increasing. So it's going to increase across the entire domain. And then finding my x and y intercepts. So this time, right, those things are not clear. So what you can do here is use a calculator to plug in 0 for x. So it's not going to get you a pretty number, but that's going to get you your y-intercept, right? Plugging the 0 in for x. You could also always just add one more column to your t-chart and throw 0 in there. If you see that it's going to cross the x-axis, and all of these will eventually cross the x-axis, right? So the only way that we have a range that goes from negative to positive infinity is if eventually it crosses the x-axis. Same is true with your y-intercept. You'll always have a y-intercept, right? So we can always throw 0 in for y to find the x-intercept. So let's take a look at each of those cases. So the y-intercept usually is a little easier to find because all we have to do is plug a 0 in for x. So there we could really just plug a 0 in for x and evaluate that whole right side of the function. So once we do that in the calculator, we come with this value -1 point. We'll round it 2 decimal places to 5.2. You always want to look at the graph, see if that makes sense. So here you can see it's crossing between -1 and -2. So that's probably a good value there. So looking at where it's crossing the x-axis now, here's going to require a little bit more algebra skills. So this time we're going to plug a 0 in for y. So to do this, once again, right, you're just taking the original function you had, f of x, remember it's the same thing as y. So all we're going to do is plug a 0 here on the left-hand side of our function in place of f of x or the y variable, and then try to solve for x. So first step still, try to isolate the radical. So in this case, we need to subtract 1 to start. Once we subtract 1, we got -1 equals 2 times the cube root of x minus 2. Then we want to cancel out the a value using some division. So once we divide here, we get this -1/2 equals the cube root of x minus 2. So in this case, we got to remember that in order to get rid of the radical, we need to take it to the power of the index, right? So in this case, we're taking it and cubing it. Once I go ahead and cube both sides, remember it's going to cancel the radical out on the right for us, leaving us just with that x minus 2 outside the radical now. On the left, once I cube the -1/2, takes me to the value of -0.125. Then one last operation to solve for x. So adding 2 to both sides now takes us to the value of 1.875. So looking at the graph again, just to see that that makes sense, right? We can see that as we look at the graph, that 1.875, you can see that the graph is crossing between 1 and 2. So that is an answer that does make sense. So you can see here, right, the graphs will always have the x and y intercept as our S shapes or Z shapes cross both axes. You'll just have to plug in a 0 for the opposite variable to solve for those intercepts. So I want you to, with your group, flip to this last one, number 11, and go ahead and try to work through that with your group. Talk through it, graph, find h and k, figure out those x values that are going to get you those perfect cube roots, right? Come up with the points, then talk about the characteristics. After that, right, once you finish, I'll go ahead and in a second post the answers here up for that last one so that you and your group can check, right? And then you'll have the remainder of class to work on the assignment. So there's the last graph, number 11 there for you. If you want to just check with your group before then working on those practice problems.